Okay, so we're going to be doing rational inequalities right now, and rational inequalities are very similar to polynomial inequalities. So what we're going to do is we're going to find the roots, but in this case we're also going to have to find the vertical asymptotes. And what we're going to do is we're going to use the multiplicity trick again. There's one thing which is a little bit different in the rational version of it, and we'll discuss that a little bit later. But for now, remember, multiplicity even means it either goes both in the same direction, both up or down, and what that means is they're both positive, both negative. Odd multiplicity means one up, one down in either direction, or it switches signs from negative to positive or positive to negative. So when we get to the part that I'm talking about, I'll discuss it a little bit more. So just like what we did before with equalities, right, what we need to do is we need to bring everything over to the left-hand side. So if I subtract 3 to both sides, we get that. Now, before we can do this, right, you need to combine the fractions into one. And that's what we did with equalities too, right? So nothing has changed from when we did linear inequalities to polynomial inequalities to rational inequalities. You just treated them like they're an equal sign and continue. Yep. So n plus 15, n plus 6. The LCD here, since there's only an n plus 6, is going to be n plus 6. So I need to multiply by the n plus 6. So here we get n plus 15 minus 3n minus 18. All over n plus 6 is less than 0. So I'll write that part out. This right here is that part. And the minus 18 comes from there. Once you have it in this form, right, we need to find the roots, find the vertical asymptotes. So the roots happen when the top, which is going to be minus 2n, and then minus 3 is equal to 0. So n is equal to 3 over negative 2, or if you want, negative 3 over 2. And then the vertical asymptotes happen when the denominator is 0 after the reduction. So there's no reduction here, and we just get n plus 6 equals 0, so n is equal to negative 6. So what we need to do now is we need to draw out the number line. So let's go ahead and do that. Negative 6 right here. Negative 1.5 is right there. So the difference right now is before we used to be able to use the degree of the polynomials, right, to determine the left and the right hand side, but we can't do that in this case. So what we need to do is we need to plug in a point. So plug in a number in one of these 3 intervals. If you can, 0 is usually the easiest one to do, but you don't need to use that. Okay, you can plug in minus 1,000, you can plug in negative 4, right? It just depends on what interval you're talking about. So if I plug in 0, 0 is in this interval on the right-hand side. So if I plug in 0 into here, does everyone see that the top becomes negative 3 divided by 6? Okay. You don't even need the numbers. All you really need to know is the sign of the top and the bottom, or the multiplications that end up happening. So there's a negative on the top, a positive on the bottom, so those two numbers give you a negative number. So out to the right-hand side, that's all negative. The negative 3 or 2 is given by this, which is a root. So what is the multiplicity of that root? It's 1. So that means it flips, right? The signs flip. So from negative, as it crosses over, it switches to a positive. This one over here, this is the vertical asymptote. And as it flips over or crosses the vertical asymptote, the multiplicity is still 1, so it changes signs. Okay. Now, you go back to the initial part and you ask yourself, what is the question asking? When is this rational expression below 3, or this one, which is what we're using, is less than 0? So we want to find the parts where it's negative. So this happens from negative infinity to negative 6, and then from negative 3 over 2 to infinity. Now, it's not or equal to, so these are both open. So you need to be very careful, okay? The difference between a rational expression and a rational inequality and a polynomial inequality is before, when you had that equal to sign, you just automatically threw in all the roots. That is true here as well, but you have to be careful because that is not a root, it's a vertical asymptote. So anytime that you have a vertical asymptote, it must always be open. The only ones that can change are the roots, so this one has the ability to be closed or a bracket if that is or equal to. So let's go ahead and do this problem. So it's already set to equal, or set one side equal to 0. So let's go ahead on the left-hand side and factor it. So the top is p minus 2 times p minus 1, and the bottom is p minus 3 times p plus 1 is greater than or equal to 0. So the roots are given by the top, or p is equal to 2, p is equal to 1. And then the vertical asymptotes are given by the denominator, p minus 3 equals 0, and p plus 1 equals 0. So here, p is equal to 3, and p is equal to negative 1. So once we have the roots and we have the vertical asymptotes, we can draw the number line. So let's go ahead and do that. So we have 1, 2, 3, negative 1. And what I like to do to help you remember which one is which is you label them. So this is a vertical asymptote, this is a vertical asymptote, and these are roots. So plug in a number. Again, 0 is here, right? It's in between the intervals, so this is going to be the easiest number to use. You plug it into the factored form. So here, if we plug in 0 there, we get a minus. Plug in a 0 here, we get a minus. Plug a 0 here, we get a minus. Plug a 0 here into here, we get positive. So in total, 3 negatives that will total up when you multiply divide to give you a negative. So in this interval where the 0 is, you get a negative. The multiplicity of vertical asymptote negative 1. As we cross over, the multiplicity is 1. So as we cross over, it changes signs. But the multiplicity of all of these is 1. Okay? So as we cross over, it'll change signs. So from here to here, it'll change to positive. As it crosses over, it'll change to negative. Then as it crosses over, it'll change to positive. We are asking the question for the values which are greater than or equal to 0. Okay? So greater than or equal to 0 is positive. So it starts from negative infinity to negative 1. Another part is 1 to 2. And then another part is 3 to infinity. Now I wrote it this way because I want to look at the endpoints, right? This negative 1, the 1, 2, and the 3. They all are different, right? Some of them are roots, some are vertical asymptotes. So the vertical asymptotes, which is negative 1 and 3, they can never be part of the solution. So they must always be open. 1 and 2, though, they're roots. So because they're roots, we need to ask, are we allowed to equal 0? And so here we can, which means we have to write them as brackets. So what this tells you, the intervals for which that rational expression is going to be positive is these 3 portions. Done.